Hello, it's Keith here, and this is lesson 15 of the Aku15 series of my Z80 programming tutorials. Now, last time we discussed how the screen is built up within the level code, but I want to go into the details of how the actual routines that do the QuadSprite, which is the Tilemap routine, and also the SolidFill work. They're both fairly similar routines. The fill routine just fills the entire screen, whereas the QuadSprite reads in 8 bytes of data and repeatedly draws onto the screen to create a scrolling tile. We're also going to have a look at the bit shift routine, and so these three are some of the main routines that draw the background, the remaining one being the gradient, which we will look at next time. So let's make a start and have a look at the actual code. Now, originally I'd wanted Aku15's episode 2 to have a full tilemap where you would have individual buildings and things that would make up the background, but it was far too slow. So in the end I settled for this very crude tilemap routine that would just allow for a 32 pixel wide tile to be repeated across the screen, and this was very fast. The reason it was very fast we'll learn now. It's because we used the stack to quickly push data onto the screen, and we actually only use 4 pushes, a total of 8 bytes repeated, and this means we don't need to do any reading of our data when we draw an entire line. So let's have a look at the actual code. So here's the code here. This is the start of the routine, and as the routine starts, the DE register will be pointing to the data for the tile, and the HL register will be pointing to the right hand side of the line. The B register will be pointing to the line count. So let's make a start. So first we have to back up the stack pointer because we're going to use the stack pointer to point to the destination for the screen data, and we do that here, moving HL into the stack pointer. You'll notice we increment the stack pointer here on the spectrum. The reason for this is I didn't want the HL register to be at the end of a byte boundary, because if you just increased L it would actually loop around. So I actually kept it 1 too low to intentionally allow the code to work fluidly without that being a problem. So that's a quirk on the Spectrum version. Now once we've done that, we then load in the memory address of the byte data using that we backed up here, and we then start reading in. We load the first pair into IX, then we load into BC, DE and HL. Once we've done that, we then start drawing to the screen. Now you'll notice the first time we push IX, but then we pop it back into AF. The reason for that is AF is much faster than IX, and we're going to be pushing this many times. You can see here's the first one, which is a bit different, but the rest are all the same. We at this point have written 32 bytes, which is the entire width of a Spectrum screen. The Amstrad screen, however, is 80 bytes, and so is the Enterprise, so we need to carry on here. So you can see here, this is one entire line of the screen, and this is completely unwrapped, which is part of the reason it's so fast. That and push commands are the fastest writing and also reading commands on the Amstrad CPC, or the Z80 rather. So now at this point we've done a full line. So what we do is we now enable the interrupts here, and we then quickly disable them again on the Spectrum. You can notice here that we actually restore the stack pointer after the enable interrupts command. This is a quirk of the Z80. If you check the documentation, the enable interrupts command doesn't actually allow interrupts to execute until after the following command. But a quirk I've noticed is on the DS emulator there's actually a bug because it obviously doesn't emulate that correctly, because I've noticed glitching occur, which is because it's actually enabling interrupts this command when, according to the Z80 documentation, it should enable interrupts at this point of this command. But anyway, just a small thing there. So here we are now calculating how to move down the line. You'll see there's 3 different versions of this code here. The ZX Spectrum version, the Enterprise version, and the Amstrad CPC version here. They're all very different, but that's what we have to do. So that's how we do it. And then when we get down to here, we just move across our byte data to point to the next line of the tile. And then we repeat it until B reaches 0. When it does, we just return after enabling in interrupts. So it's quite complex conceptually, but there's actually relatively little code here. Essentially all we're doing is we're reading in the line's byte data and then we're repeatedly drawing it, and this is why the tiles have to be 32 pixels wide on the Amstrad CPC and 64 pixels wide on the ZX Spectrum, because that's how many bytes are made up by 4 registers being pushed. So there we go. Now surprisingly, the SolidFill code is almost identical. It's essentially the same code except for there's no reading routine and we just repeatedly push DE. Apart from that, it's basically the same. So surprisingly straightforward there. But anyway, now one other piece of code I do want to quickly discuss is the bit shifting code. Now if you remember when we discussed the level data, there is no routine built into the QuadSprite routine to actually allow for pixel shifting for the parallax effect. So the way we do it is at the very end of the drawing of the background, we then bit shift all of the tiles in this code here. And you can see here, this is the code that does that. So essentially all we do is we pass a pointer to the line of data within the tile and we pass a count of the lines. Now the first thing we need to do is read in the ticks occurred. This is the level ticks, which is a bit mask of the time. So essentially, if we want something to happen every tick, we use bit 0, every other tick bit 1, every fourth tick bit 2, and so on. So we AND in the ticks occurred from the core, and we AND that with our parameter we've been passed, and if the result is 0, then we're not going to update this tile map. And if that's the case, we just move to this skip routine, which just skips all of the lines within the byte data. This means we're now in the position to do the next tile if we didn't actually update this one. If we do want to update this one, we go into this routine here, and essentially all of this is doing is it's taking the byte data of the bitmap and it's rotating the bits, but it's having to do it while understanding the combination of bits within the screen memory. On the Spectrum, it's very simple. It's just a black and white bitmap. But on the Amstrad CPC and the Enterprise, it's a 4-color bitmap. And so we have to move the bits around correctly to allow the scrolling effect to occur. And when we get down to here, we're just repeating again for that line. And then when we get down to here, we are repeating again for all of the lines within that bitmap. So when we've got to this return, we've done a single tile and then we repeat for the next tile. So it's all pretty straightforward. Now the important thing to notice is some of the levels do scroll in the opposite direction. Generally they go from the right to the left, but some of them do go backwards from the left to the right. And there is an alternate version of this bit shifter routine which is loaded in for those levels. So that's how we do the scrolling of the tile map data for the levels. That's the clouds, the buildings, and also the ground here. So it's pretty straightforward really, just a bit quirky. So there we go, that's all I wanted to cover in this episode. Next time we're going to have a look at the gradients, which are quite long and complicated. The gradients were one of the first routines I wrote for Chibi Akumas, because when designing the game, the important question was how fast can I actually do things like clear the background? Because if it's too slow, the game won't be playable at all. And so the gradient routine was one of the first things I did, and I was actually quite impressed with it because I realised that I could actually fill a gradient to the screen and have it scroll faster than the CLS command of BASIC could clear the screen. So I was quite impressed with that. Anyway, we'll have a look at it next time. Thanks for watching today, and goodbye.